Yeah, hi everyone. I hope you had a good week and worked through all the NumPy material, because this week we will be using it. We will be talking about data processing and machine learning with scikit-learn. I think it's really useful to do the coding stuff like this one in this lecture up front, because later in this course we will be using it extensively, because I really think it's useful to learn about concepts in machine learning, but then also try them out in practice and use them and explore them using code examples. And with that, there's not that much to say for this lecture, except you maybe saw that I uploaded homework 1, the first real big homework, which will be testing you on stuff that we covered in earlier lectures, like supervised learning concepts and so forth. But it will also test you on the code examples in NumPy and ask you to tinker around with the k-nearest neighbor algorithm to get a better feel for how NumPy and scikit-learn work. And with that, there's not much to say. Watch the videos, do the homework, do the self-assessment quiz afterwards and stuff like that. And while you're doing that, please also don't forget to have some fun once in a while, because my favorite season of the year just started, fall. I really like fall in Wisconsin because it's finally getting colder and the leaves begin to change. It's really beautiful outside and stuff like that. And I was also super excited last weekend. I already went to a pumpkin patch. You can see I got some pumpkins that need to be carved. So with that, let me get started with the lecture so I can then get back to my little pumpkins and get them carved for Halloween. Let's get started. Yeah, we already arrived in part 3 of the Computational Foundations lectures. Just to tell you what this lecture will be about, here's a list of the topics we are going to cover. So first of all, we are going to talk about reading in a dataset from a tabular text file, such as a comma-separated value file or CSV file, which is the most common file format for traditional machine learning nowadays. Then we will talk about basic data handling, like getting the data into shape for our machine learning algorithms and training procedures. And then we will be talking about scikit-learn, machine learning with scikit-learn. But before we do so, I wanted to briefly recap Python classes and object-oriented programming. I gave you some exercises to prepare yourself for Python or just understanding Python better. However, I think it's just useful to briefly recap what object-oriented programming is and what Python classes are, because the scikit-learn API for machine learning is heavily inspired or is heavily relying on object-oriented programming. So in order to understand how scikit-learn works, it's kind of necessary to understand object-oriented programming. Then we will talk about preparing training data using the scikit-learn transformer API. And we will also talk about defining scikit-learn pipelines, which help us chaining different operations, such as preparing the dataset, like dataset scaling, normalization, and then also dimensionality reduction, the classifier itself, and so forth. So we can define a very efficient training pipeline that connects many aspects of the machine learning workflow together to make things more convenient, which is one of the big strengths of scikit-learn. Also, I should mention this lecture I decided to make slides again. So in the last 2 lectures we talked about things using JupyterLab, and I like JupyterLab a lot, but I think it's sometimes easier to explain things if I can use my pen here or my pencil. So with this pencil here, I can just better annotate certain code examples. So what I did for these slides is I made screenshots from the JupyterLab or Jupyter Notebook, and I will annotate them in this lecture. However, the whole code notebook is also available on GitHub. I just uploaded it to GitHub. And I also added some explanations there, so you can consider this document as an optional course notes or lecture notes document for this lecture. Yeah, just a brief recap. Where are we in this course right now? So we had an introduction to machine learning, covered KNN, where I already showed you a little bit how scikit-learn works. Then we set up Python, learned about NumPy and scientific computing, and now we are going to cover data processing machine learning with scikit-learn. And then in the next lecture, we will get back to core machine learning concepts like decision trees, ensemble methods, and model evaluation afterwards. So while this is the last part in the Computational Foundation lecture series, It doesn't mean that we won't be using code in the future. However, you can consider this as like the foundation that you can use to play around with concepts we introduce later on. And you will also be implementing certain things as part of the homework. So in that way, the computational foundations are really like the tools that we will need to explore the concepts we cover later in this class. Here is again the overview of the typical machine learning workflow that we covered in lecture 1. I don't want to go over the details again because that's what we did in lecture 1. However, I wanted to highlight the main aspects of this pipeline. So there is the pre-processing part where we read in a data set, split into training and test data and so forth. And then we get to the learning part where we use this data set, the training data set, to fit a model using a machine learning algorithm. And then later we evaluate the model using the test data set, and then we can use it in the real world for making predictions. So in this lecture here, we will be talking about the pre-processing steps, and we will also get to the learning steps. Some of it will also include the evaluation. However, we will talk much more about that in future lectures. So here we will briefly talk about evaluation and when we discuss pipelines, and later on we will go back into more detail about model evaluation. So the main focus here is on pre-processing and learning. And for that, let's start at the very beginning, reading in a dataset from a tabular text file, such as a CSV file. So for this lecture, I'm using the Iris dataset quite heavily again. I know not everyone is very excited about working with Iris flowers because the dataset is a little bit old and not super exciting. However, I think there is an advantage of using a simple dataset, and it's that it gets out of the way. We don't have to spend much time thinking about the dataset and can think about the methods here, because this lecture really is more about understanding the computational tools rather than getting distracted by discussions of the dataset. So just briefly recap what the dataset looks like. So we have 150 flowers, and we have 3 classes: Iris setosa, Iris versicolor, and virginica. There are 50 flowers from each class in this dataset. So we have 50 flowers from each. And the features we have are the measurements, so the length and width of the sepal flowers and petal flowers. So we have sepal length, sepal width, petal length, and petal width. So we have a 150 times 4-dimensional dataset here. Plus, of course, the labels and labels. Personally, before I start working with the dataset in Python, before reading it in, I usually always use my terminal to explore the dataset, or at least take a look at how the first lines of a dataset look like, and also the last line. That can be useful just to get an overview of the dataset before we use any sophisticated tools, so we know which tools we have to use. For example, which options we have to choose. And this is super fast. And also note that we can do that directly in JupyterLab. So we can use this exclamation point parameter to execute terminal commands. So this is a terminal or shell command. And this head command, it's actually a little program in Unix and Linux for a terminal. What it does, it's returning the first 10 lines of a dataset or of a file. So here we can get an idea of how the dataset looks like. So if we take a brief look at it, we can see there is one row that specifies the column names. So column names are known. It's not always the case that we have the names of the columns included in the dataset. Some datasets don't include the first row with the column names. But we can also see we have an ID column which just enumerates the different training examples here. And the last column, this is our label column in a string format, and then we can see there are 4 columns with floats or decimal numbers, real numbers, and they're all comma separated. It's also important to know. So there's something we can learn by just doing this quick head command here to just get an idea of how the dataset looks like. Usually I also in practice use tail, which gives me the last 10 lines of the dataset. Then my favorite library for reading in a dataset is pandas. Pandas is short for panel datas. So I've never seen that written down somewhere, but I heard or listened to a podcast with Wes Kinney. It was an interview where the podcaster interviewed Wes McKinney, who was the original developer of pandas, and he mentioned that he named the tool after this acronym panel datas. Okay, so pandas is a data frame library, so it allows us to work with data frames. You can think of a data frame as a more sophisticated version of a NumPy array, but I bet that most of you have worked with R, so you can really think of this data frame like a R data frame, where you can also have mixed column types and so forth. So yeah, let's use the data frame library pandas to read in our dataset into a data frame. So there's one function when we import pandas that is called read CSV, and the read CSV is a very powerful function that can read in a CSV file super fast. It's evolved over many years and people made it really fast. It's one of, I would say, best ways of reading in a dataset. So here, because our file has a very nice form, so it has the CSV form where we don't really have to pay attention to anything like function arguments. We can just call the function with a file name and it will read it into a data frame. So this will be a data frame object. And the data frame object also has a head method, which is kind of similar to the head method of our terminal command here, or of our terminal. However, it's only giving us the first 5 lines. There's a way you can get the first 10 lines, but it doesn't really matter. We really just care about the first few lines so we can see that the dataset is read in correctly. If you omit this part, if you just call df, it will show you the whole data file, which is also okay. However, sometimes the dataset is very large and we don't have to see the whole file. Here it's more about seeing whether everything looks okay, if it was correctly parsing the file. Otherwise, if it's not okay, you will get some weird output here. So we can see here everything went correctly because we have all the column names read in correctly. And then we can also see it gave it an additional index column. We could have specified here an argument index underscore call, and we could have used the first index or column index for that, and then it would have used this ID column for these IDs. However, it doesn't really matter here. We don't really care about the ID here. And that, I mean, that looks great. So everything was read in correctly. And you can also see you can have mixed types. So here, for example, these are integers. I mean, you can call certain functions to check the types. However, we can already see that there's no decimal point. So this is an integer. This is a float type. You can see the decimal point. And here this should be an object or string or object type. And yeah, there's also similar to NumPy a .shape attribute. So if you use the .shape attribute, you can see the dimensions of the data frame. So in this case, it's 150 times 6 dimensional data frame, like 150 rows and 6 columns. Yeah, like I mentioned, there are many options for the read CSV function. You don't have to memorize any of that. However, if you have problems with reading in a dataset, it's worth exploring those. For example, there's the SEP here, which stands for separator. In our case, we are working with comma separated files, so we put a comma here, but it could also be, for example, /t if we work with tab separated files and so forth. So it really depends on how our data file is formatted. Then we have, for example, a parameter for the header. So it's automatically set to infer, so it kind of guesses whether we have a column header or not. If that doesn't work, For example, if we have a file that doesn't have this row here, so if this is not included and we have problems with reading in the data set, we can try, for example, setting this to none, and then it should usually always work. Yeah, the index column I mentioned, we can set it to 0 in this case because we have actually an index column. We can also just set it to none, so it will create an index starting at 0. It doesn't really matter in most applications if we are aware what the index is, but in this notebook, for example, or in this lecture, we are not going to work with the index, I think. So there's also use call, which means use column, so it's specifying which columns to use. I will show you an example where how to use that in the next slide. And there are other ones like skipping rows, how many rows to skip, and the number of rows to read in total, and many other options. Yeah, so what do we do if we have a very large data set that is exceeding our computer memory? So here's an example code that I wrote like, I don't know, 5 years ago or something, when I was working on very large molecular property files. So I had a data file that had like 100 million lines of molecule data, and it was like molecular properties like the weight of the molecule, the number of hydrogen acceptors and donors, and things like that. And I had a very small computer memory. I think I had a MacBook Air with like 4 gigabytes of RAM, which was not really much. So in that way I had like challenges working with a data file, especially if I wanted to work on my laptop. So there's a way, for example, you can use the arguments in pandas to work with large data sets. Later, next slide, I will show you some other ways, but this was one way of doing it. And also note that nowadays there is some iterator function that is also useful for that, I think. So, but the way I was doing it here was I was defining a chunk size, and the chunk size was how many lines of the data frame or the CSV file I wanted to read in one iteration. And then also to make the file smaller, or the data frame smaller, I only read in those columns that I cared about. So that was, for example, the molecule ID, so the name of the molecule, the partial charge of the molecule, whether it's currently purchasable or not. So drugs now means basically whether you could buy it or not. How many hydrogen bond acceptors and how many hydrogen bond donors. So I think originally the file had like 10 or more columns, but so I think that the file had like at least 10 or 15 columns, but I didn't need all of the columns, so I only specified 5 I cared about. And then I was also getting the total number of lines in the CSV file, how many rows it had. So it was a little bit too large to open it, let's say, in Excel and count, or let's say flip to the last row. So there's a way you can do that in Python. You can just iterate over the lines, like using like opening a file and then using read lines, or just iterating over the files line by line. However, that took also a long time if you have 100 million rows. So what I did is I was just using this terminal command, which is vc minus l. So wc minus l. W means so wc means word count, and minus l means line. So this will just give you the number of lines, and then of course the file name, which was, let's say, my large.csv file. I could have executed that in pandas directly using this exclamation mark thing. However, the problem with that would be it would be printing the number of lines. However, I wanted them assigned to a variable. So I was using this sub process module, which is spawning off a Python sub process in, let's say, the terminal using check output. So that is executing a terminal command, which I put here. And then I was just splitting the output, getting the first value, which is basically the number of lines. So here I was just using this terminal command to get the number of lines very efficiently. And then I was iteratively reading the CSV file. I was actually reading this into an SQLite table, but doesn't really matter here. Let's say I was just iteratively processing the CSV and in each iteration I was doing something with the data frame in the data with the data in the data frame. So in each iteration I only read 100,000 lines out of the 100 million lines. How did I do that? So I had this range iterator here. I set it so to start at 0 and then going up to n lines, where n lines would be something around 100 million. And I had an increment size or step size of chunk size, which was 100,000. So if I would execute that, that would mean, for example, the first one would give me a 0. So I equals 0. And then in the next iteration would be I equals 99,999. And then it should be I equals 199,999 and so forth. And then in each iteration I was specifying, of course, the file name I cared about. I didn't care about the header. And then I had the number of rows. So here this is how many rows in total it should read. This was 100,000. And how many rows it should skip. So that means in the first iteration it would read the first 100,000 rows. In the second iteration it would skip the first 100,000 rows. Because in the second iteration we would start here, and then it would read the next 100,000 rows and so forth. And I could do that then to process the whole data file, even though the data frame didn't fit in my memory. So I'm showing you that here because it's just a nice illustration of how we can use these pandas function arguments for the read CSV function. However, there are also more efficient ways of using a pandas-like API for large data sets that don't necessarily fit into computer memory or are very slow to process. So one of them is the Modin project, which is following the pandas API very closely. So it's kind of like a drop-in replacement of pandas. So you can just import modin.pandas as PD instead of importing pandas directly. Of course, you have to install Modin first, but if you do that, the API will be the same as the pandas API. And last time I checked, they cover 90% of the pandas API. And they basically implement functions to make pandas run faster on multiple processors, and I think also out-of-core processing, which means it doesn't load all of the data into memory at the same time and so forth. So this would be one option. And another nice option is Dask, which is a very established project in the Python scientific computing community, and it also really has a lot of options. If, for example, if we use a cluster of multiple computers, we can set the number of workers, the number of threads per worker, how much memory to use, and stuff like that. So it's really also a cool tool if you work on a cluster, let's say CHDC cluster or something like that at our university, then you can use Dask or Modin. Both have a very similar API because they follow or try to follow the pandas API. Yeah, this was all I wanted to say at this point about reading in data. So it was mainly about the pandas read CSV function when we have a data set in a CSV file format. However, in practice, you may encounter other file formats, but I don't want to discuss all the possible file formats right now. There would be a very long list of file formats and possible ways files are formatted. But I hope, this was just a very basic introduction that gets you pretty far, because nowadays, for example, if you look at Kaggle and stuff like that, most data files are in a CSV format. In the next lecture, we will then discuss how we can process the data set further once we have it in a pandas data frame.